Hello guys, how's it going? Mike coming back with another video on number theory. In the previous video, we looked at factorial notation, binomial coefficients, also known as combinations, Pascal's triangle, and the binomial theorem. In this video, we're going to begin with chapter 2, and we're going to begin with a very important algorithm. It's called the division algorithm. This algorithm is very, very basic in its statement. However, it's very, very important because we're going to be using this guy as the basis for several future topics in this course. We'll be seeing subsequent algorithms that require the use of this guy. We're going to be seeing those later on in this chapter, later on in chapter 2, as well as in subsequent chapters. And really what this algorithm says, it says that if we have two whole numbers, a and b, and typically when we do this, we say that a is greater than b, we can divide the integer a by b such that we get a quotient and we get a remainder that is less than b. And there's a particular way that we write these four numbers: a, b, the quotient, and the remainder. So at the top here, we have the statement of the division algorithm, which says, given integers a and b, with b being positive, and we also typically assume that a is greater than b, there exists integers q and r such that a is equal to q times b plus r, where r is greater than or equal to 0, and r is strictly less than b. The integers q and r are called the quotient and the remainder respectively. Now, this is obviously referring back to very, very basic math that you learned back in, say, primary school. Say we had 10 and 3. If we tried to do 10 divided by 3, we would, back then, we'd write 3 and 1/3. We'd write a mixed fraction. That 3 was called the quotient, and that 1, what's in the numerator of that fraction, was called the remainder. But now we're going to look at just a slightly different way to write that. But it does help to get used to writing things in this particular form because we're going to need to write things in this form for later on in this chapter. So just doing a couple more quick samples and working with some slightly larger numbers. Let's say that a was 1,000 and say b was 30. So 1,000 equals, I want to be able to write this as something times 30 plus something else. So the question is, how many 30s can we pull out of 1,000? Well, we can pull 33 30s out. So that is 33 times 30 is 990, and we are left with 10. So that 33 there is our Q, that 10 is our R, the 30 is my B value, as you can see, and the 1,000 is my A value. A equals Q times B plus R. And note that R is greater than or equal to 0, and it is strictly less than B. Doing one more sample here. A is equal to 450. B is equal to 15. $450 equals. Question is, how many 15s can we pull out of 450? Well, we can pull out 30 We can pull out 30 15s, and 30 times 15 is 450. So 450 is equal to this 450 plus 0. My remainder, my quotient, my b value, and then my a value here. In this particular case, r is equal to 0, which is certainly okay. That is very possible. Now, in the statement of the division algorithm, we said that we were typically assuming that b is positive. We can still use this. We can still do the same thing if b is negative. The only difference is that r is going to be less than the absolute value of b. We still want to have a positive remainder. It's just that this remainder will be less than the absolute value of b. So just a couple very, very quick practice problems you can do on your own. For each of these two samples, I give you an a value and a b value. Use the division algorithm to write a in q times b plus r form. So there are two quick samples. I'll let you do those on your own just for some nice, quick, easy practice. Now, one of the uses that we're going to use for this division algorithm is to prove various facts about numbers that take on certain kinds of forms. But first, before we do that, we're going to establish a couple of useful definitions that arise from this division algorithm. If, in the statement of the algorithm, if I let b equal 2, then any whole number a can be written in the form of either 2q or 2q plus 1 for some whole number q. Why is it only 2q or 2q plus 1? Because our remainder has to be strictly less than b, and it's going to be a whole number. So the whole numbers that are less than 2 and greater than or equal to 0 are either 0 or 1. So it's either 2q plus 0 or 2q, or it's 2q plus 1. And if you plug arbitrary whole numbers, q, into each of these two forms, you'll get a particular kind of number. If you take any whole number and you plug it into the form 2q, you're going to get all even numbers. If you take any whole number q and you plug it into 2q plus 1, you're going to get all odd numbers. So from this, we define even and odd numbers as such. We say that an integer a is even if a is of the form 2q, where q is some whole number, and likewise we say that a is odd if a is of the form 2q plus 1, where k is any whole number. So using these particular definitions of even and odd, we're going to do a small proof of some nice facts about numbers. They're a little bit obscure, they're a little bit out there, not necessarily the most useful things that you will draw from for your future math classes, but still just being able to prove some really basic facts or properties of some numbers can be pretty nice. So we're going to use these two definitions to show that the square of any integer leaves a remainder of 0 or 1 when you try to divide it by 4. So what we're saying here is you have some whole number, a, square it. You'll get a squared. What this claim is, and what we're going to try to show, is that if you take a squared and you divide it by 4, then what you're going to get is something of the form 4q plus 0, aka 4q, or 4q plus 1. You get something that's either 4 times some whole number or 4 times some whole number plus 1. And we're going to break this down into 2 cases. We have the case where a is even, and we have the case where a is odd. So let's first work with the case where a is even. If a is even, then from our definition, a is equal to 2 times some whole number. Now, I wrote 2k. You could write 2q, but as you go through the problem here in the notes, you see that q comes up later. So just don't use the same letter, but you have free choice as far as what letter you want to use. So a is equal to 2k for some integer k. So if I square a, I'm squaring 2k. When I square 2k, I get 4k squared. And this is of the form 4 times some whole number plus 0, or 4q plus 0. In this case, q is just k squared. K was a whole number, so when you square whole numbers, you still get whole numbers. So if a is even, and we divide a squared by 4, we get a nice whole number. We get a remainder of 0. If a is odd, then a is of the form 2k plus 1 for some whole number or some integer k. So if I square a, I'm doing 2k plus 1 squared. If I FOIL that out, I get 4k squared plus 4k plus 1. And now, this is where we do something a little bit odd, not something that we typically do when it comes to pulling terms out of quadratics. In just these first 2 terms here, there's that common factor of 4. So I'm going to pull the common factor of 4 out of just those first 2 terms. So that's why we have this guy right here, 4 times the k squared plus k plus 1. Now, the question said that we want to show that a squared will be of the form 4 times some whole number or 4 times some whole number plus 1. So that's what we want to show. And we can do this now given where we're at right here. We assume k was some arbitrary whole number. So products of whole numbers are whole numbers, and sums of whole numbers are whole numbers. So this k squared plus k here, this is all some whole number, which I called q. So a squared is of the form 4q plus 1. 4 times some whole number plus 1. Where q, which as we just said, is our k squared plus k, is an integer. So we've now worked with both cases, and in each case, we've shown what it is that we wanted to show. If your integer is even, you get a remainder of 0 when you divide it by 4. If your integer is odd, you get a remainder of 1 when you divide it by 4. Therefore, we have shown what it is that we wanted to show. Now, this is just one particular sample problem in this category of problems, which I'll call it, that will come from this particular section. In the next video, we'll be doing more sample problems to see how we solve a particular kind of problem. That type of problem will typically be phrased something like this. Use the division algorithm to show that the square of an integer or the cube of an integer or just something like that is of the form 8k or 8k plus 1 or 8k plus 3 upon division by some number, say 10 or something like that. But you'll see in the next video, when we go through several sample problems, you'll see the pattern that is coming up, and it'll be pretty clear what it is that you have to do. So this was just a little bit of an introduction into this chapter, a little bit of an introduction into the division algorithm, helping us get our feet wet with how we're going to be using this guy for later on in this chapter, as well as later on in our course. If you have any questions or comments, be sure to drop them in the comments section below. Otherwise, until the next video, take it easy, folks.